Our last speaker this afternoon session is Devin Petersohn, and he's a software engineer at Snowflake, and he's going to talk about everything we need to know about dataframes.
Thank you. So the title of my talk is "We Don't Data Frame Shame." It's okay to use your favorite data frame. You don't have to pick one just because your friend tells you that it's good. All right. So a little bit about me. I have an unusual route to getting to where I am today. I went through the Marine Corps to get to undergrad. I did a PhD at Berkeley. My thesis was titled Data Frame Systems Theory, Architecture, and Implementation. So I've studied data frames a lot. I like data frames a lot as well. And there are all different kinds of data frames, which we'll get into. After my PhD, I co-founded a company. And that company was acquired by Snowflake, where I currently work. So we do a lot at Snowflake around data frames. But mainly today, I'm going to be focusing on open source and kind of general data frame isms. So if we take a look at the current landscape, this is a tiny, tiny view of a tiny, tiny number of all the tools that are available to you if you want to just interact with data or play with your data. We have data science and data analytics, and typically those are siloed off. They're separate. Data frames often live in the data science space, but a lot of data analytics tools and a lot of data analytics companies have a data frame as well. So a lot of organizations end up looking like this. So you start, Pandas is just an example here, but you start with a small scale tool, prototyping, exploring, looking around at your data, trying to figure out what you want to do with that data. Then when it comes time to actually scale it, you move to a big data tool. In some companies this is Spark, in other companies this is some data warehouse or a SQL-based tool. But that forces a rewrite. Then to move to production, sometimes that's yet another rewrite. And so you have this big kind of loop here where at the end of it, if something goes wrong, because something always goes wrong in production, you have to basically go all the way back to the person who wrote the original workflow and say, hey, there was a bug in your logic or something like that. This causes a huge amount of pain and time, and it's very confusing, right? Because the big data tool that you're using might even have a data frame. Pandas is a data frame. Spark has a data frame. Why aren't they working together? Why aren't my assumptions at this scale the same as the other scale? We're going to dive into a bit about what data frames actually are. So if we go back to our tightly coupled APIs here, you know, this is what kind of this disconnect is causing a lot of this friction. And so what we want to try to do today is try to make sense of all this. What is going on here? How can we kind of compare one tool to another? How can we compare one data frame to another and do so in a way that's fair, but also, you know, makes sense from like a good first principles perspective? Okay, and so the natural first question, if we want to answer this, is what even is a data frame? Well, a long time ago, in our very, okay, yeah, this is a Star Wars reference, but at Bell Labs, that's where a lot of cool software came from in these days. They were doing research in statistics and writing a programming language called S. And they had a problem in that group in that they needed their arrays to be able to support multiple different types of data. They also needed to be able to label their experiments and that kind of thing. So effectively, they created what we use today, or what we know of today, as the first data frame. This came in S in 1990. It was released in this book. You're welcome to go and buy it if you want. But I pulled out the little excerpt here of, you know, what's interesting and what's relevant from like a data frame's perspective. And you can see here that the idea is generally to try to kind of bring some of what we use in databases over to the kind of world of arrays or matrices, which is typically what statisticians had been using at the time. So data frames, you can see here very clearly and very intently, data frames support matrix-like operations but they also have these kind of like table-like features. This is very interesting because it kind of means that data frames aren't tables. They're not databases in that respect, at least as they were intended to be in the initial implementation. So things started, and S eventually was open sourced as R, and R kind of became stable in 2000. The number of operators is a very, very rough estimate here because R is more of a functional language and has a different way of interacting with data frames than you would do with pandas. But then when it came to pandas, pandas became a community development, and a lot of operators were added, a lot of functionality was added, a lot of integrations were added, and so we ended up with very, very powerful tool in pandas that all kind of stems from and kind of is inherited from S originally. Okay, so back to our question. What even is a data frame? Well, if we want to understand what a data frame is, we're going to try to understand it from first principles. I'm going to talk about the data frame data model. I'm going to talk about data frame algebra. There's a little bit of math, but don't worry, I will warn you before there's math, so if you don't like math, you can just turn off your ears or something. And then then we'll talk about parallelism and decomposition rules. This will be relevant when we kind of try to compare tools later. Type system and operator semantics, excuse me. We'll touch on a lot of these things, but the purpose isn't to go too deep into any one of them. It's really to kind of give us a framework upon which we can start to compare the features and functionalities of different tools. Okay, so formalizing the data frame. So this is something that I worked with a rock star group at UC Berkeley. Many different professors and grad students all contributed to this. And basically what we did was figure out what a data frame is and write it in formal language. Okay, the math warning is here, if you're not worried. There is some parts of the Greek alphabet on this page, so just be warned. Okay, there it was. Now, I'm just going to explain it to you in ordinary people terms, not the kind of like very formal math. So data frames are ordered, but that means but not necessarily sorted. So that means you can have like a user specified order. Users can order things in whatever order they want, and that order can be maintained throughout the workflow effectively. So each operator, given an input order, has a deterministic output order. Rows and columns are ordered. So that kind of goes to the symmetry and the matrix-like features that were inherited from S. Another key point here, in comparison with databases, no predefined schema is necessary. So normally when you define your database, you define a schema first. You say what the types are of every single column, and then you put the data in afterward. In a data frame, you don't have to do that. You can just have it be an unspecified type or an undefined type, and those types can be determined at runtime. You can also have column and row labels that have types. This would be like the pandas index that we're all familiar with. And those labels, or that index object, can become data. Indexing by row or by indexing by label or by numeric index is also possible. This is another one of those hybrid features that came from matrices. So you have like name notation, which is indexing by label or selecting row by label, and you have positional notation, which is selecting based on position, right? The fifth row or something like that. Okay, so to dive just one layer deeper, we're going to compare to things that we're all familiar with. The first thing is linear algebra and matrix objects. So a data frame is a heterogeneous matrix-like data structure. It's not a matrix because it has different types in it. It can support both numeric and non-numeric types, and it has column and row labels. Matrices do not, of course. And you can index by label, like I just mentioned, in addition to position as you normally would with a matrix. And it also has support for relational algebra operators like join. So a join, there's no such thing as like a join in a matrix. It doesn't really make sense to have, like, what would that even be? But in a data frame, you can have a join. Okay, so if we look back at our original S specification implementation, we this is pretty pretty true to the original implementation. This formalism is. And again, the formalism's purpose for the purposes of this talk is to kind of help us compare against between different tools. Okay, now if we take a look at the relational database or the relational algebra perspective, data frames are an ordered table. They have named rows of arbitrary type. You can select based on that named row. A lazily induced schema. Again, the schema doesn't need to be defined up front in a data frame. You can figure it out at runtime. Column names can be arbitrary type, and it has column and row symmetry, so it's transposable. A database is typically not transposable, although you can pivot. And then support for linear algebra operators like matrix multiply, which are very, very difficult to do in a traditional database. Okay, so for this part of the comparison, I'm going to try to bring it up a level. I know it gets a little bit dry when I start talking about the low-level comparisons, but we're going to do a fun comparison here. Talk about something that we all like, food. I think we all like food. So if we look at our traditional relational database, a traditional relational database is a lot like a Michelin star restaurant. You have a curated menu. You can't order off menu. You have a very specified experience. It's very tailored. And you get what you get. But it's highly, highly optimized. Now, if we look at a data frame like pandas, a data frame like pandas is a lot closer to a food court, where you kind of get to pick and choose what you want from different areas. So in a food court, you can do something really, really interesting, like sushi and French fries. Something that's not what I would choose, but you can do that, right? And in the same way, you can do a lot of things with data frames that some people might not choose to do. So data frames are really just that flexible. And so looking at this from a bit of a higher level, when you're writing queries in a database, you write the entire query once, and then you send it off. And in a data frame like pandas, you can incrementally build up your query and inspect intermediate results. This is like writing a query, doing a print afterward, or something like that. So in terms of flexibility, databases have a very strict schema, and of course, I've already talked about some of the schema differences. You can also have mixed types. There's row column equivalence. Metadata can become data, et cetera. And then databases are also not very versatile. Of course, they give you this very curated experience, like I mentioned, but you're pretty much limited to select from where. Whereas with pandas specifically, you have over 600 functions that you can choose from to kind of help you build your query. And each of these things comes with trade-offs, of course. Okay, so that's the data model at a high level, and now we kind of understand what the pandas data model is, how it compares to other things that we're generally familiar with, and what the kind of nuanced differences are between pandas and some of the other things that we might use. Okay, so the next question is naturally, what can a data frame do? And so the next steps are to define an algebra. Now, I'm not going to go through the math part on this one. I'm just going to kind of talk about at a high level about what we can do with the math. So pandas has over 600 operators. I mentioned that. There are a lot of things that pandas can do specifically. But what we were able to do, the group at Berkeley was able to narrow it down to 15 operators. And this 15 operators can be basically applied along columns or rows. This is in contrast to databases, which only apply along rows. So one good example of this is you can drop a column based on a filter based on some condition of that column. So let's say you want to drop columns which have a 80% null or something like that. That's one query in pandas. That's two queries in a traditional relational database. Okay. And so if we break down this set of operators that I've been talking about, we have ordered versions of relational operators, group by, sort, join. These are the things that you're used to using in your database. We have MapReduce style operators, MapReduce, explode. We have metadata manipulation operators, which are somewhat unique. Infer types, filter based on types, to labels from labels, and then we have some matrix and linear algebra sourced operations. This would be like your transpose and your mask and concat. And so this, believe it or not, this set of operators can represent everything that pandas can do. And I'm happy to kind of talk about afterward, if you want to come talk to me, I can point you to the paper where we talk a bit more about that. But this set of operators does completely cover all of what pandas can do. Okay. The next steps are to formalize parallelism. So if we want to start comparing a system like pandas to a system like Spark, we need to understand how Spark parallelizes the data, how that would compare to what we would want to do if we could parallelize pandas in the most effective way. And so we basically went through all the operators that we had defined, and we broke them down into different types of operators. And the important part from this is to understand that there are two major classes, the row-wise and the column-wise, in terms of parallelism that you can do with data frames. Cell-wise is another operator, but cell-wise is kind of a generalization of you can effectively apply cell-wise along row-wise or column-wise. So it's kind of a generalization of those. But effectively, row-wise and column-wise are the two key things. So when you're writing a data frame implementation, if you want to effectively parallelize everything, you need to be able to parallelize both along rows and columns. Okay. And then we also went through and did other foundational work in terms of like type system and order semantics and that sort of thing. Okay. So at this stage, we effectively know what pandas is, what a pandas data frame is formally. We know what types of operators it supports, a set of 15 that we can use to kind of look at other implementations. We know how these operators map back to pandas, and we know how to handle pandas data frame types. We know how to decouple logical and physical order and maximally parallelize each operator. So now we can start to look at other implementations and see kind of how they all compare. We can start to think about functionality and trying to understand why it's so difficult to take something written in one language, parallelize it with something else. Okay. So let's take a look at Spark. Who here is familiar with Apache Spark? Okay. So super brief introduction, because I didn't see everyone's hands. So Spark is an open source data processing engine that processes across a large number of computers, a large number of computers called a cluster. And basically, Spark has a data frame, and Spark is often what is used to parallelize jobs in companies. So when I mentioned that big data tool before, often that is Spark. And Apache Spark's architecture is pretty heavily inspired by a relational database. So you can see here I've kind of broken this one data frame out into multiple different computers. I did my best to show the partitioning here, and you can kind of see that the one logical data frame is split up across multiple different computers. Each computer has its own subset of that data. And so if we look back at the parallelization rules that I was talking about, this type of parallelism does not support column-wise operators. So anything that requires strict column-wise partitioning is not going to be natively supported out of the box in pandas, or excuse me, in Spark. Another interesting feature of Spark is that it has lazy evaluation. So this is just a fun meme, but I wanted to talk a bit about what lazy evaluation is and what it means and why it exists. So normally in our normal everyday Python programming, we're using Python. Python is an imperative programming language. Basically, when I write something, the computer does that thing. We can contrast this with a declarative language like SQL, where I write something and then the computer basically does whatever it wants because it knows better than I do how to execute and get the result that I actually wanted. So on the right, we have basically query planning, query optimization is possible. On the left, it is not. Lazy evaluation turns imperative programming into declarative, kind of. So basically what it does is you write something and nothing executes until you write some trigger word, and then execution is triggered. And so that gives the system the opportunity to kind of build up a query in the same way that, with SQL you would write a really giant SQL query. Okay, and if we look at the kind of data frame features that I mentioned in pandas, and we compare that with Spark, we see that Spark has a few missing. And so, looking at this, you might think, well, that Spark is not as good or something like that, but that's not the case, of course. Should we just use pandas? Of course not. We don't data frame shame. Apache Spark is a distributed system. It can handle scales that pandas can't. People use them together all the time. It's really important to understand where these tools are useful and understand the tool's capabilities. Okay, polars. Who here has heard of polars? Okay. Okay, so polars is a data frame system. It's written in Rust. It's fast, of course, backed by Apache Arrow. It has a clean, opinionated syntax, a lot fewer operators than the 600 operators that exist in pandas, but still very, very powerful. And if we take a look at this, polars has also made the decision not to have an index object, but it does still let you select based on row number, the same way you would with an array. So not all of the metadata operators are there, but the majority of them are there. And so polars is written in Rust. It's very fast. Should we just use polars? No, it's okay to use pandas as well. Pandas is still widely used, has broad support in the ecosystem. There's a whole ecosystem around it. Polars is, of course, growing, but pandas is still okay to use. I want to say, okay. Okay, now, all of this said, does this mean we should never learn a new data frame system? Of course not. We don't data frame shame does not mean that we don't learn new systems or that we don't try new things. The whole idea of not data frame shaming is to understand how these systems are useful, when they're useful, and try to use the right system at the right time. Okay, so this is probably the question that you all came here for. What is the best data frame? The best data frame is pandas. No, I'm just kidding. So the best data frame is obviously the one that solves your company's needs. Now, this is the most important thing. None of the other criteria matter. If it solves your company's needs, sometimes that's based on some cost profile. Sometimes your company doesn't want to spend millions of dollars. Sometimes they do want to spend millions of dollars on a system, and they just want you to get it out fast. It's very important that you pick the tool that solves the problem that your company has or that your team has. Now, among those, after that, if everything else is equal, then it's good to use the tool that you're most productive with. LLMs are changing everything, so who knows if this advice is really any good anymore. But the idea here generally is to try to be as productive as you can. Yes, and then of course the one that your friend knows or your teammate knows. These are of course good. It's good to have people you can go to ask questions, and then the one that you have to learn from scratch. It's always good to learn new things, though, of course. So. This is, of course, in the context of you trying to solve a problem within your company. Yes. Okay. Okay. So with that, I will happily take any questions. And thank you all for coming to my talk. And yeah.
Okay, we've got plenty of time for questions now.
Did I speed through it? I'm sorry. I went a little fast through that.
Did your grad level research with your group give you any hope that pandas could be simplified by putting things in terms of these 15 things instead of us having to learn 600?
Yeah, that's a great question. So, so there's always hope. So the 15 operators, the thing that I should say about that is that set of 15 operators is not going to be very handy for a user because it heavily relies on things like transpose and things like map, and it's very hard when you're trying to write something like, as an operator. it's hard to write something and reason about transposing and moving data around and that kind of thing, using maps and UDFs very, very commonly. A lot of the things that exist in pandas exist there for convenience. But absolutely there is hope. And I think Polish is a really good example of kind of trying to narrow that down and drill it down into a smaller subset that's still extremely useful, but still kind of achieves a lot of the power that you get from the data frame construct as a whole. So yes, there's hope. The change will probably have to come from outside of pandas, because at this point pandas is too big probably to change significantly. There's millions of lines of legacy pandas code, and every change, like rightfully so, every change is scrutinized and that kind of thing. It's very difficult to remove things from the pandas API. So yeah, but yes, I do think there is hope. At Berkeley, we teach an entry-level data science course, and one of the things that we do there is we have like a version of pandas that is not the full power of pandas. And so, yeah, I think there's hope. I think that we're kind of recognizing that, not everything is always required in pandas.
Any further questions?
So, looking at the history of data frames specifically, it seems as though it was easiest to get data into pandas, and then that became the thing the API people expected. And when people wanted to do stuff like, out of core or data that's larger than memory, we kind of had to lead them to we had to build the infrastructure around that problem, rather than it was probably you needed a separate tool, right? Because it's not obvious to me that you should use a data frame API for a distributed computation. So do you think that in the design space of tools, it's useful for APIs to unify, or do you think they should kind of just disintegrate and we should have here's how you do distributed, here's how you do EDA, exploratory data analysis, and here's how you do stuff that's larger than memory, et cetera? Or do you think there's value in having a grand unified API for data frames?
Yeah, yeah, that's a big question. So, so databases have SQL, but if you've ever used more than one database, you know that SQL is not standardized and that each one supports something else. I think that any effort to kind of try to standardize data frames will probably fall into a very similar kind of situation where you have joins and all these things that everybody supports, and then you have specialized things that these highly optimized or niche systems support. I don't think that's necessarily a bad thing, but in terms of standardizing on APIs, yeah, it's difficult because when you standardize on APIs, you also have to standardize on the expected output. And so, one of my grad projects was a system called Modin, which is a distributed pandas implementation. And it's just a hard problem to try to match an existing API and also match the behaviors, because you have to answer even simple questions like, how do you handle differences in floating point arithmetic, right? Do you always give the same number of floating point decimals for system A as you do for what you're trying to match? So these types of standards, I think it's a very, very hard problem to try to standardize on any API itself. We do see standards coming in the form of Apache Arrow, for example, on the memory side and on the storage side. I think that is a really good level to standardize on. When you start getting at the user level, I think it gets a lot harder. Any other questions about data frames? Or you can ask me anything. Oh.
This is an awesome talk. This might be a noob question, but when it comes to distributing the actual work of a data frame versus a SQL-like job, at its core, you're basically just implementing similar like operators and then just executing some kind of plan, or is there something that's unique between the two?
Yeah. Yeah. So let me walk back here. So when you think about distributing operations, like data frame operations specifically, having to distribute for something that supports all of these different types of access and has different requirements for what other data is on the same node or in the same location, this is a much harder problem than doing like a traditional relational database style row-wise operation or row-wise data distribution. Because in this case, you have to think about, there's a lot more shuffling involved. This is partially why it's so difficult to make pandas scale, if that makes sense. We spent a lot of time at Berkeley working on this problem. How do you lay out partitions? How do you structure your partitions in a way that you're not constantly shuffling data and make sure that the data's in the right location? So if we go back to the operators, so a lot of these operators, the way that we ended up, I probably actually have a slide somewhere, but the way that we ended up structuring the partitions was in Modin specifically, and I'm not here to talk about Modin. This is more a theoretical talk, but this is a pretty very rough and very, very old. A lot of these slides came from my dissertation talks, and that was several years ago. So, but we ended up doing more of like a block-oriented or more closer to a column store because the challenge of being able to parallelize row-wise and column-wise in the same system is it's just extremely tricky. In addition to being able to kind of transpose the data at will and that kind of thing. So I don't know if I answered your question fully.
Pretty good.
Okay.
Any other question?
How well supported would you say the Parallel Pandas library is? Because I found I only decided to look I looked up Parallel Pandas full disclosure just recently, and it and that is and I've seen that as and what I saw is an attempt to kind of get around the like the single execution that people typically expect of pandas.
Yeah. So can you restate the question again? I'm sorry.
How well supported is Parallel Pandas?
Oh, the library that I was talking about? Oh, I'm not here to self-promote or promote that library or anything like that. I really just wanted to talk about data frames. But it has 10,000 GitHub stars. It's been downloaded a lot of times. It's widely used. Yeah, so we've been working on it for many years. Yeah.
Nice.
Yeah. I think we have one more here in the front.
So this is related to my previous question, but if you didn't have to inherit the baggage of the past and you were to redesign something that looked like a data frame now, without any of the S stuff or the R stuff or the Panda stuff, what do you think that would look like?
That's a great question. So yeah, so it would probably look a lot like what we designed theoretically. The challenge came, the major challenge came in the actual implementation and trying to match Panda's behavior and that kind of thing. But the usefulness of being able to have something that kind of is some weird marriage between relational database world and statistics world, it's super, super useful in the modern age where, we use PyTorch and all these other machine learning libraries. Data frames are very, very useful in the statistics world. So a lot of the APIs would probably drop off. Polars is, I'll say Polars is a very good implementation. It's still okay to use pandas. I know, it's okay if you use pandas, really. But I think Polars is a great implementation. Yeah, I mean, it would need to be distributed and scale and all that kind of thing. But yeah.
Last question.
So this may be frosting. It's not about computation per se, but I work with multidimensional data quite a bit, and there Xarray shines.
Yep.
Xarray borrows a ton from pandas.
Yes.
But one of the nice things about Xarray, beyond the multidimensional aspect, is so a column maps into a variable. It's metadata, that you can freely add metadata to a variable, as well as the entire data set. That's one of the things I dislike, at least about pandas and any other data frame that at least I've worked with. What's the status in data frame thinking of being able to enrich it in a standard way so that you can add easily metadata to each column, and so that it carries over as computations are made or transformations are made?
Yeah, that's
things that, like, right now you only have data type and a column name. A long name, units, other background, anything you like, it's extremely useful.
Yeah, absolutely. So that's a good question. So enriching it with metadata, it falls slightly outside of my past work, of course, but extremely useful, as you can imagine. So the interesting thing about being able to enrich the columns. This is such a good question. I'm sorry. The interesting thing about being able to enrich columns is that right now what you would have to do is basically hold a separate data structure that maps somehow to your columns or your rows or however you want to annotate your data in that way. This very closely matches the kind of early implementation in S of having like or like that predates S, where if you saw my kind of back in my day, where basically you had your 2D array, or maybe you had a few arrays or something like that, but you had a separate data structure that was your labels, right? And so yeah, I'm sure that things will converge, but and one day you will be able to have a data frame where you can properly annotate things, if it doesn't already exist. I don't know everything, of course, but yeah. But yeah, it is an interesting parallel to the early implementations of data frames that were kind of just, not a lot of syntactic sugar and just kind of like, here's my array and here's my labels. And they're totally separate data structures that you have to, like, you as the programmer have to handle and manipulate. So yes, and Xarray is very good at that. So yeah.
Okay. The very last question. Sorry.
Thank you. I'm just going to ask very random questions. Do you have any very solid metrics to compare different data frames, data types? I mean, and also just curious, what have you tried? I assume you have tried all different kinds of data types. Like NumFOCUS has pandas, polars, Databricks has Spark, and then NVIDIA has cuDF and GPU accelerated polars. So sometimes, I mean, GPU accelerations does not necessarily beat the CPU-based Spark. It depends, right?
Yeah.
So what do you think of them?
Yeah. So that's a bit of a complicated question. And it's a really good one. So the purpose of this talk was to look at things functionally and to try to evaluate them functionally and go from first principles. Can system B do the same thing as system A? A totally separate question is, how do we even benchmark these systems that have totally different capabilities and that kind of thing? And that is a very hard problem to answer. Of course, I've run benchmarks. I mean, when you're a PhD student, you do a lot of benchmarking and running a lot of experiments. So yeah, of course I did. I've run all of them, at least all of them that are shown here. But in terms of like how to standardize on benchmarking, I think that's an unsolved problem. I think it's a really, really hard problem too. And I don't think somebody who wrote a data frame is necessarily the right person to write the benchmark, because everybody knows individually how to, what you have a bias no matter what, right? Like I wrote this and so I can, I can accidentally or on purpose show some benchmark that shows mine in a better light, or I can run it enough times, or I have the benefit of optimizing it, and et cetera, right? So it's a hard problem. And when you're evaluating things for your company, it's important to evaluate them in the environment that they're going to be run in. If you don't do that, then you're going to get skewed results, and yeah. So when you're dealing with products and companies and that kind of thing, there are whole teams that exist to kind of help support migrations and help support evaluation and that kind of thing. So if you're evaluating this in the context of like a company, there are systems in place to kind of help with that too. But yeah, it's much harder if you're just trying to figure out which one to use at a given point or something like that. Which one's faster? The answer is it depends, and it's always it depends. So.